Thank you very much. So I actually read the instructions for the EFT seminar series, and I was required to specify what my EFT would be and what my new parameter is going to be. And so I'll say it right now. We're going to try and modify quantum mechanics itself, the actual Schrodinger equation, and try to add nonlinear terms to the Schrodinger equation. And you will see how this happens in the next few slides. All right. First of all, why would we want to modify quantum mechanics? What's the actual motivation for it? If you think about it, quantum mechanics was the theory that was built on various observations based on the 1900s. And literally the rules of quantum mechanics, a bunch of people got together in a hotel room or a conference center and then said, these are the rules of the world, right? That's just what happened. And if you think about the axioms of quantum mechanics, a good number of these people didn't even believe all of them. They were fighting with each other the entire time, asking if these rules even made any sense. So why should we think that a bunch of rules written up by a group of people is somehow the absolute truth, that it can never be changed? It's worth asking that question. How solidly convinced are we that these rules are absolutely correct? So what are the rules that one could change? So in my opinion, quantum mechanics really just rests on two postulates. Everything else you can derive from it. The first is that probability is a fundamental aspect of the description of reality. And the second is that the theory is linear. From these two things, you can derive all of quantum mechanics. The question becomes, if I want to modify quantum mechanics, which of these do I want to modify? There's a lot of work on people trying to modify quantum mechanics, and they typically try to modify probability because people are uncomfortable with the notion of probability as being a fundamental part of describing the world. In my opinion, trying to go after probability is not a sensible thing to do, and I'll tell you why. Why do we have probability in quantum mechanics? What is the fundamental reason why probability is essential in quantum mechanics? This comes down to the fact of two observationally true facts about the world. First of all, we know that if I take a finite system, such as the hydrogen atom, and if I ask how many energy levels does the hydrogen atom have below some given energy level, it's finite, right? The world has ground states, in other words, and there's a finite number of states that a system has below any given energy level. That's a fact about the world. Otherwise, you won't have sensible thermodynamics, it turns out. The second is the fact that the world has continuous observables and symmetries. That's also a fact about the world. Notice that these two things are actually going to give us trouble if we insist that every observable of the theory is always deterministic. In other words, if I insist that every observable of the theory will always give me well-defined answers, I'm going to prove to you that these two concepts are in contradiction with that. So here's a simple example. Could an electron in an atom have a well-defined position? When I was a child, I always thought of the electron as going around the proton like a solar system, right? Where that's a simple model of the atom we all have as children, where there is the electron with the well-defined position going around the proton in a circle, right? That's how we think of it typically. Suppose that concept made sense. And by sense, I basically mean this electron has a well-defined energy as it goes around the proton in this atom. If that was a sensible quantum state, I could now apply a rotation to this system, rotation being a continuous observable and symmetry of the world, which would take me from this state to this state, right? And if both of these were separate, well-defined quantum states of the theory, from one initial state, I've now gotten another initial state. From one initial quantum state, I've gotten another quantum state. And if they both have well-defined energy, of course, I now have two states that have the same energy. And indeed, I could now apply this continuous rotation and therefore end up with an infinite degeneracy of states, right? So that, of course, is in contradiction with my assumption that that a finite system must only have a finite set of energies below a given energy level. So quantum mechanics essentially is a compromise. It sacrifices this notion that every observable of the system is always completely deterministic, right? By sacrificing that requirement, quantum mechanics is able to preserve these two facts about the world, that I have a finite set of energy states and have continuous symmetries and observables. So if you look at various proofs of how the world is quantum mechanical, these are things like the Bell inequalities, the Koch-Specker theorems, the SSC theorems. All these things are fundamentally playing off this basic fact. So if you think about the Bell inequalities, which you may be familiar with, the way the Bell inequalities typically work is that you look at some number of angular momentum states, and the world only has a finite number of angular momentum states. On the other hand, you can make measurements of rotation in an infinite number of ways. So given the fact that you only have a finite number of angular momentum states, if you make measurements in an infinite number of possible directions, it is not surprising that you can find a contradiction between the predictions of quantum mechanics and what you would expect from classical physics. So all of these proofs of quantum mechanics are basically statements that the world has to have probability. And I would say if you're trying to get rid of probability, you have to fight these two facts about the world, and I don't think you will succeed. So in my opinion, going after probability is not a good use of time. Second thing is linearity. Linearity in quantum mechanics is the statement that the wave function does not interact with itself. What does this operationally mean? Let's look at the hydrogen atom and let's think about the 2s and the 2p levels of hydrogen. The 2s and 2p levels of hydrogen are actually exactly degenerate in standard quantum theory. The degeneracy is only broken by things like the Lamb shift, right? If you think about it naively, that's a little confusing because you would say that, look, the 2s electron is this nice spherical ball. The 2p is this dumbbell. If I think about the electron cloud around the atom as some kind of a charge distribution, some kind of a classical charge distribution, naively, you would have thought that the 2s spherical shape would interact with itself due to the electron self-energy or something, and give rise to a contribution that would depend upon the shape, right? So you naively expect, if you thought of it very classically, the 2s and 2p levels of hydrogen would have a contribution to their energy that depends upon the shape of the electron cloud. And that is just not true in quantum mechanics because the theory is linear, the wave function doesn't interact with itself. But it's not like there is some fundamental rule of physics that says the shape of the electron cloud must be something that I cannot observe, right? Clearly, if I put another electron in the system, that electron is very sensitive to the exact shape of this electron cloud. The 2s electron here, for example, will do a better job of screening the nucleus than the 2p electron here. So it's not like there is some fundamental reason why the shape of the electron cloud is something that one cannot observe. So the question now becomes this: why can't the electron feel itself, right? What are the challenges in writing down a theory that would allow this kind of nonlinear interaction of the electron cloud with itself? The main issues that come up are issues of causality, measurement, right? These are two things of quantum mechanics. And basically, one can also ask a question, how does all of this fit into quantum field theory, which we, of course, know is a fundamentally correct description of nature. So let's ask why causality may even be a problem in a nonlinear theory. So the main issue is the following, right? Let me just do something very dumb and take the Schrodinger equation, I d psi dt equal to the linear Hamiltonian, HL, the usual Hamiltonian we're used to, times psi. And now I've written down a nonlinear term, okay? Some psi squared plus psi star squared. Great. For a single particle, this is all fine, right? This is just a single particle evolution, no big deal. You can show that nothing complicated actually happens in this theory. The crucial problem is that quantum mechanics fundamentally has to deal with entangled systems. If you have entangled systems, you can now write down a more complicated wave function, psi of x, y at t, two particles at x and y, and I can write down this complicated entangled state where I have a particle at x entangled with a particle at y with different wave functions, alpha I and beta j. Okay, that's just an entangled state. And now you're going to use this nonlinear equation to time evolve the system forward. The question you want to ask is the following. I take two particles. One is with me. I take two particles on the Earth. I create some entanglement between them. And now I take one particle, retain it on the Earth, and the other particle, I'm going to take it to the moon. And say someone on the moon now performs a local operation on the other particle. When I perform a local operation on the other particle, some kind of local unitary operation, what that will do in this wave function psi is that it will send alpha I to some unitary multiplication, right? Which means all the coefficients that are living in front of this guy will now change. This alpha I will become some linear combination. All of them will, of course, change the coefficients that are sitting in front of the beta j, obviously. Now, if you have a time evolution of this kind, psi squared plus psi star squared, you can convince yourself that if you just simply perform that local operation on the moon, because you're changing the coefficients of the term sitting in front of beta j, the time evolution of beta j, which is, say, the particle that is with me on the Earth, will immediately change. because I've changed these coefficients, right? So you will therefore say, if this happens, this theory is not causal because a local operation in the moon was immediately changed the way my quantum system on the Earth was evolving. So that's not a causal theory. So that's the concern. Of course, it's not like non-linearity automatically has to create a causality. We know of plenty of examples of causal nonlinear classical theories. And in all of these cases, the way you enforce causality is by a Green's function, right? That's what happens, where you say, as long as there's a Green's function, if I change something and it only propagates via the Green's function propagator, you are guaranteed that the system will respond causally. So here comes the main set of ideas that allows us to modify quantum mechanics in a causal way. The key point is the following. Linear quantum mechanics is basis independent. We don't care about position or momentum or whatever. I can always come up with linear quantum mechanics like in any basis, because linearity tells you I don't care about any basis at all. On the other hand, we know there's a fact about the world, which is that interactions in the world are local. They care about position. And so the position basis is a preferred basis when it comes to thinking about interactions. Position basis is also the natural way in which we use field theory. And if you think about it, if I'm worried about problems with multi-particle states and stuff like that, which is exactly the problem in trying to naively come up with a nonlinear modification in quantum mechanics, field theory has been designed as a natural way for us to actually put in multi-particle states while taking care of causality. So this tells us that perhaps instead of trying to modify the Schrodinger equation at the single particle level, let's go full on and try to modify quantum mechanics at the level of field theory itself. So this is a bit unusual from what people normally do. We usually think about quantum mechanics as some uber structure from which we derive field theory. But here I'm going to take the other point of view, which is that if I'm worried about things like causality and stuff like that, I'm going to say, look, field theory is in fact the correct description of the world. Let me try to put in nonlinearities directly into field theory. So with that, let me give the outline of the rest of my talk. I will begin with the framework and tell you how to introduce these nonlinearities. So we'll talk about how to modify field theory, obtain the single particle Schrodinger equation from it, describe both causality and measurement. After that, we'll talk about the phenomenology of this theory. Unlike linear quantum mechanics, it turns out nonlinear quantum mechanics has some tremendous macroscopic effects that are truly dramatic. We'll talk about that. Then we'll talk about experimental constraints on these theories, as well as current tests that are ongoing to actually test this particular framework. It'll also turn out that unlike linear quantum mechanics, nonlinear quantum mechanics is extremely sensitive to cosmology, which is a very interesting fact of the story. And then I won't have much time to discuss that in detail, but it's extremely important. And I'm happy to talk to anyone about it after the fact, and then we'll conclude.
May I ask a question?
Here's the framework. Yes.
Can you go back to your trial linear nonlinear term slide?
Yes.
So in that trial linear term, if you instead put in epsilon psi star psi, presumably you come into no trouble with causality, right?
Epsilon psi star psi. Yes, exactly. That's exactly what's going to happen, basically.
Yeah, because I'm just thinking about the Schrodinger-Poisson equation, which
right.
basically is a nonlinear Schrodinger equation, and that's the basic structure.
Yeah, and so exactly. So what we're going to learn from this is that there are specific terms you can add, and they're okay. So let's do the framework itself. So I'm going to directly go into the Schrodinger picture of quantum field theory, where, I usually give these talks to people who are not EFT experts, but you guys obviously know it. In the Schrodinger picture of quantum field theory, obviously what we are doing is we are time evolving some Fock states. Some quantum states, they're created from some Fock bases or whatever. There's simply some quantum states of fields. My operators are time-independent operators. And then I have a Hamiltonian, which is simply the integral of some Hamiltonian density that depends upon the field and its conjugate momentum. And in quantum field theory also, we are simply solving the Schrodinger equation, I d chi dt equal to h chi. The point being that h is this Hamiltonian made of these operators. That's basically what we're doing. So I'm going to do something a little unusual than what people normally do. I'm going to derive the Schrodinger equation from an action. So this is not the usual action of quantum field theory. I'm just creating this little action because it helps me put the nonlinearity more easily. So notice that I can obtain the Schrodinger equation by taking this particular action and demanding that the correct solution to the equation of motion is the path that minimizes this action. It's just a dummy action that I've created. And you can trivially see that if you perform the Euler-Lagrange procedure from this action, that will tell you, oh, the correct quantum state you're going to evolve to is the one that obeys the Schrodinger equation. This doesn't buy you anything in normal quantum field theory. But let's play this game. Let's think about how a Yukawa theory fits in the story. So I'm going to take this Hamiltonian, and I have the Yukawa coupling Y and my field phi and psi bar psi, the usual scalar, and the fermion. So in this action, this fake action that I created, the way this Yukawa theory will fit in is basically that there's this Hamiltonian, and I'm taking this expectation value of the state, which is what gave me what I wanted. And so this Yukawa theory looks like this, right? I basically say this Yukawa coupling, Y, phi, psi bar psi, sits in this Hamiltonian. So I'm basically taking the expectation value of this operator, phi of x, psi bar of x, psi of x, sandwiched between the state chi of t. That's what it is. And so if you put all the things properly, you end up getting that, okay, the Yukawa coupling is simply the expectation value of chi, phi, psi bar psi, chi sitting in this action, whose minimization gives me the Schrodinger equation. So in quantum field theory, what we've been doing for the last 100 years is to write down nonlinear terms in the operators. So nobody would complain about me putting a phi square over lambda, for example, psi bar psi, higher dimension operators, and going and studying them. Great, this is what we've been doing. So these are nonlinearities in the operators, but of course linear in the states. We never change the number of times the chi appears in this particular expression. These are nonlinearities in the operators, but not in the state. But this form, when you look at it, suggests a natural extension, but I can say this is all linear quantum field theory. At the nonlinear level, what I can do now is basically obey this rule. The action needs to be a number. And what I have now are two vectors sitting in here and a bunch of matrices. There are, of course, other ways in which I can get a number out of the story. So what I can basically do is I can look at this guy and realize, look, I can put an expectation value here, right? So I can take, instead of taking chi of t, phi, psi bar psi, chi, I can now say, let me put a chi of t, phi of x, chi of t, psi bar psi, chi, right? That's again, just a number that comes out of this story. There are ways for me to break these operators up and put in these kinds of numbers. This is now nonlinear in the states as well. So that's basically our main idea, that you can take your quantum field theory action and look at any interaction there, and you realize it's possible for you to now stick in states in this particular way, and that will now lead to state-dependent quantum evolution because your terms are now nonlinear in the states as well. That's the basic idea. And we're going to analyze this theory perturbatively. I'm going to analyze the nonlinearity perturbatively. So let's think about how it works. Let's simply look at the theory of the Yukawa theory. And let's look at how the time evolution of the fermion psi is getting modified by this nonlinear term. So I have my usual Yukawa coupling Y, phi, psi bar psi. And what I did is I put in my nonlinear term, which essentially sticks in an expectation value of the operator phi in the quantum state psi. And that's now sitting in front of how the fermion psi will evolve. So once again, I'm simply going to use my rule that the path of minimum action was supposed to give me the Schrodinger equation, which now simply tells me that, oh, when I have my new Schrodinger equation for this nonlinear term, this guy will now be sitting in front of psi bar psi. So once again, I'm just doing standard stuff. Now, perturbatively, we know that at zeroth order, this is just standard quantum field theory. We all know how to solve this problem. This is the Yukawa coupling interacting with the fermion. Sorry, a scalar field interacting with the fermion. Now, if I want to compute the first order correction, which is basically how I'm introducing this nonlinearity in this perturbative way, what we will be doing is basically using the zeroth order solution, okay, for this expectation value. We will put that and then compute the first order correction. So of course, at zeroth order, I've computed everything using linear quantum field theory. I've obtained my state chi. Okay, I know the operator phi. I can now compute this expectation value. The way this expectation value now enters in computing the first order correction is that this expectation value simply looks like a background field. It's just a C number field that's sitting in front of psi bar psi. And of course, we now know how to perform standard QFT on this background field in order to compute the first order correction. This, of course, applies to all orders, because to compute a term of given order, I only need to compute terms of lower order, and all the lower order terms will only enter as background fields. I'll make a quick statement about causality, and you can kind of see why this essentially works. Non-linearity in this story is entering via an expectation value. At lowest order, of course, the theory is causal because this is just standard QFT. And an expectation value of a field is, of course, an observable of quantum field theory. So standard quantum field theory ensures that the expectation value that I put in, okay, to compute my first order correction only responds causally. Specifically, if I take my system and particle A and particle B go a long way away, and I change something about particle B, the way that changing of particle B affects particle A is via the expectation value of this quantum field phi, and that expectation value only evolves causally, right? And because now my first order correction is causal, you can again do this perturbative argument to basically show that there is causal evolution at all orders. One can go through this in detail, but I'm just giving you the basic idea for why it should be true. So let's now look at the phenomenology, okay? If I have a single psi particle, how does the wave function of the single psi particle evolve once I put in this nonlinear term? Well, again, to zeroth order, psi just sources a phi field. I can go ahead and compute its expectation value. What does it look like? Well, if I gave you a wave function for the psi particle, okay, the expectation value is just simply the fact that the psi field has some charge blob, right, like the scalar charge, and then I simply go ahead and compute the Green's function that comes out of it. The expectation value, which will simply look like the following. It's the integral d4 x prime psi star psi g. Someone mentioned that psi star psi looked like it had the right properties to give you causality, and now you immediately see why it appears that way, right? In the story, it just naturally follows that what appears in the sensible way is just a psi star psi, with of course a Green's function if you're interested in time as well. So that causal Green's function and the psi star psi business together is going to ensure that the whole theory will remain causal. Of course, you're not surprised by it because the expectation value of phi better be a causal thing in linear quantum field theory. So now we can ask this question: how does this look like in for my psi particle? So the key thing we are learning now is that the single particle equation that we are getting depends upon the field theory, right? So the equation that you write down here depends upon whether it's a Yukawa theory, phi-4 theory, or whatever it is, because of simply the nature of how I introduced this particular nonlinear term. So for the Yukawa theory, the way the fermion behaves is the fact that it's now got the integral d4 x prime psi star psi with this Green's function sort of sitting there. So you can go ahead and calculate what this thing will do. So if I gave you say some kind of atom where the electron was interacting because of this phi particle, right? There's now going to be a nonlinear interaction in the system where I'm basically going to realize that because of this particular term, when I have this electron sitting here and this electron sitting here, these two shapes are different. And because of this term, this guy can talk to itself. And you will now find there will in fact be a breaking of the degeneracy of the 2s and 2p levels of hydrogen because of the self-interaction. You can prove many other things pretty easily, that the Hermitian form of this Hamiltonian that I've given to you means that I can preserve the norm of the theory. It allows you to maintain probabilistic interpretation, all that kind of stuff. Let's talk about entangled systems and how causality works for entangled systems. So now we have this particular fact that I have given you this complicated entangled state, psi of x comma t. It depends upon this complicated entangled state. How do multi-particle systems evolve? Well, multi-particle systems will evolve in the same way, right? All I need to do is compute this particular expectation value given this split state, and that's how they're going to talk to each other. And you can just go ahead and write down what it looks like. It basically looks like the fact that if I compute the expectation value for this complicated state, this is how it looks like. There is a bunch of psi star psi sitting in front, and there's a whole bunch of Green's functions. And the Green's functions simply say, oh, I'm going from x1 to x, x1 to y, y1 to x, y1 to y. They're all additive, right? That's what you expect. If I have this complicated state, whatever it is coming from this guy, it basically acts in this very split way. If you go and compute what expectation value looks like. This is very important because the story of nonlinear quantum is that Weinberg tried to write down a theory of nonlinear quantum mechanics, And he wrote down some term like psi square plus psi star psi. And sorry, he wrote psi square plus psi star square in terms of that kind. And he wrote that for a single particle state. And Polchinski pointed out that if you write it as psi square plus psi star square, the way I wrote it down earlier, that theory will not be causal when you actually have these kinds of entangled systems. And from very general principles, Polchinski argued that, look, this does not mean nonlinear quantum mechanics is necessarily acausal. He said nonlinear quantum mechanics can be causal if these nonlinear terms enter in this very special way. The special way being that they're all additive, right? So what we are seeing here is that the way one particle affects the other particle is through a sum of these kinds of Green's functions, as opposed to products of states. Products of states end up giving you a causality, while these kinds of sums give you causal behavior. That is basically what Polchinski argued from very general grounds. And what you now see is that that form is very natural in field theory. Let's now talk about things like measurements, right? This is an important part of the story. Measurement in quantum mechanics is not some mysterious process, even though when we teach this to undergraduates, for some reason, we do that. I don't know why. We have understood measurements very well for the last 50, 60 years. It just gives rise to some discomfort for people, but deal with it. So here is what measurement is in quantum mechanics, right? What we do when we do measurement is the fact that we take some initial quantum state, we bring it in contact with some measuring device. The measuring device and the quantum state, they interact with each other through the regular rules of quantum mechanics. The Schrodinger equation predicts the time evolution of this system. The Schrodinger equation in general will say that if I have this state, it will evolve into a linear combination of, say, spin up and this particular guy going to the left, and spin down and this particular guy going to the right. That's a prediction of quantum mechanics, right? So this is what happens when you realize that a measurement is no different than taking one quantum system and interacting that with another quantum system. Quantum mechanics predicts that you end up getting this linear superposition. Okay, this gets a stupid name of many worlds of quantum mechanics, but in fact, it's just a prediction of quantum mechanics. What is true is that if you take this particular entangled state, and if this particular state is some macroscopic system, it very rapidly gets entangled with other degrees of freedom in the universe. And therefore, it becomes true that you can no longer see interference between your different quantum states because of the fact that this macroscopic state rapidly becomes orthogonal to other states. And therefore, if you're only focusing on this particular quantum state and not the full quantum state, you can interpret the physics of this particular quantum state as a sum of many separate worlds. So effectively, this is what the collapse of the wave function is, which is a statement that when you're no longer looking at this full quantum system, the behavior of this particular quantum state alone is effectively that of the wave function collapse of Bohr, right? But this is what quantum mechanics predicts. We're not going to change this at all in talking about nonlinear quantum mechanics. Measurement will still be the statement that I'm going to take some quantum state, bring that in contact with some measuring device, and then I'm going to allow the Schrodinger equation to tell me what actually happens, which is what Schrodinger equation is supposed to do, interaction between two quantum states. The Schrodinger equation will now tell me that I can go into this general time evolution and get these particular superposition. There's an important issue between linear quantum mechanics and nonlinear quantum mechanics, which is that in linear quantum mechanics, because the theory is linear, all you ever have to do to predict the outcome of some interaction is to know the basis vectors. So specifically, if I want to measure this quantum state, which let's say has two basis vectors, spin up and spin down, I need to know that. And then I need to know the basis vectors of a measuring device, which is either spin to the left or spin to this dial to the left or dial to the right. Given those basis vectors, I can now design a Hamiltonian between these two guys, which makes it so that when these two guys interact, this design Hamiltonian that I created will create this particular entangled outcomes. That's something that I'm able to create, right? So I can pick these states so that these two different states of the pointer are orthogonal to each other. In nonlinear quantum mechanics, I don't know, in nonlinear quantum mechanics, the whole point of measurement is that I'm given an unknown initial state. But now the nonlinear Hamiltonian itself depends upon this unknown initial state, right? Which means that if I just give you an initial state, which I don't know what it is, and some measuring device whose basis vectors I know, the point is, given that the specific interaction between these two guys will depend upon the unknown quantum state, I cannot guarantee that the pointer states of this particular measuring device will always be orthogonal to each other, right? Because interaction can mix them together, which means in general, if I take my initial state, I can get something very similar to regular quantum mechanics, that is at order epsilon equal to 0. All of that makes sense. But at order epsilon, I will in fact end up getting a mixture of whatever initial quantum state I got, as well as some complicated states of the pointer, right? I can make error, in other words, because I can't guarantee that the final states are always going to be orthogonal to each other. So fundamentally, the notion of measurement in nonlinear quantum mechanics will have some notion of noise that's tied to this.
And just to clarify, so that is just what you call measurement noise is in some sense very similar to what you might call a bad measuring device, because this is that right?
Yes.
Right, because this right arrow that you draw on here is not guaranteed. Quantum mechanics doesn't guarantee that it goes into this particular superposition. It's just for a good measuring device, you don't get the off diagonal tails.
Exactly.
Yeah. Okay.
Yeah, it's more like it's possible in linear quantum mechanics to come up with a really good measuring device, right? But with no measuring device, at least theoretically, with no measuring error, at least theoretically. Here I'm saying it's not possible, even theoretically, to come up with a quote unquote really good measuring device, because you'll always have some mess there. All right. So far we have talked about Yukawa theory. But given that idea, it's actually easy to extend this sort of nonlinearity into gravitation as well as ENM. These theories, of course, as you guys well know, more easily formulated in the path integral language than in the Schrodinger language due to issues of gauge invariance. But really what you're saying is that I can now take my path integral of say QED or something, and I can add these expectation values as background fields in this particular theory. You can do it both at the interaction level as well as at the level of the kinetic term as well. And then it sort of works essentially, is the same story. You can also do that for gravity by basically introducing these expectation values as background fields in your path integral. So the story basically moves forward. With that, let me talk about macroscopic effects of nonlinear quantum mechanics. So far in my talk, you've been listening to me, and I sound like at least a partially reasonable person in that I'm starting with equations and I've just put in well-defined terms and I'm computing modifications due to the well-defined terms. So now when I start talking these macroscopic effects, you might wonder, poor guy, Surjeet, totally lost his mind in the pandemic, right? Went completely crazy. The truth of the matter is I've been crazy a long time. The pandemic had nothing to do with it. And for the specific things that I'm going to tell you about now, the craziness is not even due to me. It's not even due to the nonlinear quantum mechanical terms that I've added. The craziness really just arises from linear quantum mechanics itself. It is just that nonlinearity will allow us to sample some of this craziness. Okay. So as far as I'm concerned, all I'm doing is taking this very well-defined theory that I wrote down. You saw what the action is. You saw what I did. You didn't even complain very much about it. And I'm just computing the consequences of these terms that I've added there. So let's talk about this craziness. And it really will start from linear quantum mechanics. That's where it really begins. It's not really from the nonlinearity itself. So let's do this following experiment, okay? In linear quantum mechanics, suppose I give you a spin that's along the x-axis. Let me give you an experimentalist and say there's a laser that the experimentalist has got, and the laser has two photodetectors, one to the right, one to the left. Okay, that's the initial state of the theory. It represents the full quantum state, spin, experimentalist, laser, photodetector. Our goal is to create a macroscopic superposition. I'm not trying to create a quantum coherent macroscopic superposition. That's extremely difficult. I'm just trying to create a macroscopic superposition, and that is trivial to do. The trivial way in which you create a macroscopic superposition is that you can measure the spin along y, and depending upon the outcome, I'm going to send the laser along different directions. So what does that mean? I take the spin along x, measure along y. If I get spin up, okay, the experimentalist sees he got spin up, he sends a laser to the top. If he gets spin down, the experimentalist sends laser to the right. Okay, we all agree we can do this. The crucial point is that I'm a many worlds guy, right? This is what quantum mechanics predicts. What quantum mechanics predicts, if you think about it, is that what happened in the story is that the spin was along x initially. The experimentalists turned on an interaction, which, due to the Schrodinger equation, predicts that the final state of the theory is the following. Spin was up, the laser went to the top, and there's some environment that got entangled with the laser being at the top. Spin came down, the laser went to the right, and there's an environment that got entangled with the laser being to the right. This is extremely important. Quantum mechanics does not predict that the state is either this or that. Okay, that is this collapsing of the wave function, Bohr, whatever. It's just not what quantum mechanics predicts. Quantum mechanics predicts that the state is this full linear combination. Very important, prediction of quantum mechanics. In linear quantum mechanics, given that this is our quantum state, we can ask which photodetectors light up. I won't go through this in detail. To all of you guys, this should be obvious. The statement is simply the fact that if I'm in the world where the spin went up and the laser went to the top and I got entangled to the top, right? You know that in that world, if I'm trying to figure out, does the photodetector on the right light up? I'm computing some transition matrix element. And basically the point is, because of the fact that the environment, okay, is what it is, you will find that if I compute the expectation, the transition matrix element of the A mu operator, and I evolve it at the point, at x right, this particular point, that guy will be 0. And because that guy is 0, the photodetector at the top will light up, the photodetector to the right will not, it will be cold, and vice versa for this case. But, right, it is in fact the case that if I compute the expectation value of A mu, the A mu operator in the state chi, the full state chi, right? Remember, that full state is created by quantum mechanics. This expectation value is non-zero, both at xt and x right, right? Because the state chi contains both the worlds. It contains this world and that world. And now when I take its expectation value, the expectation value of A mu at the point, let's say x right, okay, is non-zero because it is non-zero here. Very, very important. In linear quantum mechanics, that was useless to you because its expectation value was not something you could measure because you got entangled in some way. The nonlinear quantum mechanics, I've added my new term, epsilon chi, A mu chi, okay, state-dependent nonlinear term, which now means that in both these worlds, these expectation values are non-zero, as we just said. That's just a statement about linear quantum mechanics, not even nonlinear quantum mechanics. It's just a statement about linear quantum mechanics. What that now means is that in the world where spin was up and the laser went to the top, I will find that this photodetector now lights up at order epsilon because the expectation value of chi, A mu chi was non-zero. That's true even in linear quantum mechanics. But at the nonlinear level, at order epsilon, I'm now able to sense it, right? That in other words, what you're learning is that this world where the laser went down and the spin went down, the laser came to the right, is now able to talk to this world over here. Okay, so this is again something that Polchinski realized, is that he said if you create this particular kind of nonlinearity, which really is due to causality, you will now end up creating what he called the Everett phone, right? That despite environmental decoherence, what this now allows you to do is to have these two different worlds communicate with each other. Now, this is weird, okay, definitely, undoubtedly, but I don't see anything fundamentally logically inconsistent with it, just very strange. So with that, let's now talk about various constraints on this particular theory and current experimental tests ongoing. First, what does this do to the Lamb shift, right? The Lamb shift is known to 13, 14 digits. So you might naively think, of course, this dude's theory is constrained very, very well, right? So let's think about what my theory actually predicts, and this will turn out to be extremely important. So let's take the proton. The proton is now at fixed location. Suppose I do the following experiment, right? Yeah, So let me take a proton and fix it to a particular location. I'm going to hammer it, okay? When I hammer it, and then I have an electron sitting around it, right? It is indeed the case that the 2s and the 2p levels have different charge distributions in space. And in my theory, this is nonlinear coupling, they'll have different expectation values of the electromagnetic field, and therefore there will be a large shift to the levels proportional to order epsilon. Okay, so naively you think the Lamb shift will in fact give rise to a large change to the energy levels of these two guys. There should be large level spreading. But notice that in my theory, what actually enters is the expectation value of the electromagnetic field. That's what actually appears in front of this electron operator J mu. Here's something extremely important. In linear quantum mechanics, we are very used to doing the following. We are trying to solve the hydrogen atom. We go to the quote unquote center of mass coordinates, which allows us to decouple the center of mass motion from the relative coordinates, right? And then we just solve for the relative coordinates. We ignore the center of mass completely. What this means is the following. If you take two different center of mass states of hydrogen. So in the first state, let me take hydrogen, put that in a micron-sized trap. In the second case, let me take the hydrogen atom and spread that to the size of the galaxy. Let me now measure the energy of hydrogen. No matter what the center of mass distribution of the wave function, whether the hydrogen atom is localized to a micron or spread to the size of the galaxy, you will get that the ionization of energy of hydrogen is exactly the same thing, 13.6 eV. In linear quantum mechanics, you were able to go to the center of mass coordinates and decouple the center of mass completely from the physics. And so the energy of hydrogen does not care about the center of mass wave function. Okay? You cannot do that in nonlinear quantum mechanics, because in nonlinear quantum mechanics, what actually appears is the expectation value of the electromagnetic field. That's what appears in front of J mu, which now means that if I take, for example, an electron and say the hydrogen atom, and I spread it over a micron size versus, let's say, the size of the galaxy, the expectation value of the electromagnetic field is vastly different. In the case of the micron splitting, it's of course all localized here. In the case of the galaxy, that electromagnetic field from a single charge is now spread over the entire size of the galaxy, which means the expectation value of A mu is extremely small. So crucially, what this means is that this thing that you're used to doing all along in linear quantum mechanics, where you decouple center of mass motion from relative coordinates, you cannot do that in nonlinear quantum mechanics. In fact, for the Lamb shift specifically, if you use a neutral atom, the limits completely go away, because if you take a neutral atom, the neutral atom is not sitting at localized at 1 angstrom, right? The neutral atom is now spread over a micron in a trap. That's basically how we measure the Lamb shift. We go to some trap and the atom is localized to some micron size region, and then try to measure its energy. So if you take an atom and you spread it around a 100 nanometer size, you basically realize that because the atom is in fact neutral, the expectation value of A mu is actually 0. So even if this nonlinearity was fundamentally large, the way you have measured it completely kills that bound. So it turns out that the best limit on this thing, that these Lamb shifts, they really are not very constraining. People have tried to measure Lamb shifts with ions, and even the ions are not very localized. So it turns out that even though naively you might have thought this should constrain nonlinearities at the level of 10 to the 13, because of the spreading, the bound is only about 10 to the minus 2. It sort of similarly kills bounds on QCD and gravity, things of that kind as well. The key point being the following, right? We are used to normally thinking about quantum mechanics for atomic systems and nuclear systems, etc., because that's where we discovered it. And people have tried, in fact, to look for various nonlinearities in these kinds of systems. But the main point is that because of our intuition from linear quantum mechanics, where the center of mass motion never matters, in all of these atomic and nuclear experiments, we have never tried to localize the wave function of the atom or the nucleus. Since you have never tried to localize the wave function, these nonlinearities get very damped, because in all of these systems, these wave functions actually are pretty spread out. So the leading constraint on this theory at this point basically comes from an accidental fact. We have trapped atoms. So if this parameter epsilon is actually positive, then essentially what will happen is, we have trapped ions. What will happen is that if epsilon is positive, since the wave function is interacting with itself, there will be a large Coulomb repulsion. Okay, so if epsilon is positive, the fact that we have trapped ions in a trap puts epsilon at 10 to the minus 5. For negative epsilon, where the attraction is attractive, there isn't even a real limit, because we haven't really probed these systems that well to actually go and see if there's a bound at all. But the point is, even though all of these current searches are not constraining at all for this theory, it is not that it is difficult to search it. it turns out it's actually very easy and interesting to go and search for nonlinear quantum mechanics. And let me tell you about the 3 experiments that are actually currently ongoing to go and search for this nonlinear theory. So here is the first. A version of this is being done by my friend Alex Sushkov at Boston University. So here is what Alex is basically doing, right? You take a spin and you say along X and you measure it along Y. You get spin up or spin down. And here is what you can imagine doing. You have a squid in your lab and a precise magnetometer. And if you get spin up, what you're going to do is you're going to turn on a magnetic field, let's say between time 10 o'clock and 10:10, and you'll turn off the magnetic field between 10:10 and 10:20. If you got spin down, you turn off the magnetic field between 10 and 10:10, and you turn it on between 10:10 and 10:20. What you now do is basically, if you got spin up, you turned off the magnetic field between 10:10 and 10:20. You then ask in your squid, are you now getting some non-zero magnetic field between 10:10 and 10:20? Of course, that magnetic field is not coming from the B fields in your lab that you turned on. It's really coming from the magnetic field in the other world that is leaking in at order epsilon. That's basically what you're testing. You can do a similar test for gravity, where what you can basically do is, depending upon the outcome of a spin, you can take an accelerometer and a mass. Okay, and let's say between 10:10 and 10:20, between 10 and 10:20, between 10 and 10:10, you have your accelerometer, you bring a mass close to the accelerometer. In the other world, you take the mass away from the accelerometer, and then between 10:10 and 10:20, you do the opposite, which now means that in the world where the mass was moved far away, you now look for the mass in the other world leaking into you at order epsilon. It's the same kind of idea. That's basically what you're testing. That will be done by my friend Jason Hogan at Stanford. Okay. Another experiment that's going on is at Berkeley by Hartmut Hafner. And this is somewhat a more conventional experiment, where what you're now going to do is you're going to take an ion, you split its wave function, okay, and then you recombine it and you look for a phase difference, a very simple ion interferometer setup. In linear quantum mechanics, this arm of the ion does not interact with the other arm of the ion. There is no interaction between the wave function. But now what's going to happen is basically that the Coulomb field of the one ion on this track, the Coulomb field of this path will now interact with the Coulomb field of the other path. Okay. And what is interesting about this particular setup is that the amount of this interaction depends upon how much of the ion was on one path versus the other, right? So for example, if I put 99% of the ion here and only 1% of the ion here, this guy will not have much of a Coulomb effect on this guy, right? Because of the way I've split it. So what this gives rise to is what is called an intensity dependent or a contrast dependent phase shift in this experiment. Because in linear quantum mechanics, this effect is completely absent. You never get a phase shift that depends upon what fraction of the ion is here versus here. And this is very helpful in combating systematics because all the sources of noise that you have in your experiment, they will not care whether you actually have P versus square root of 1 minus P square, right? They don't care about how much of the ion is in one part versus the other. They only care about overall phase shifts in the full experiment. So you can use intensity dependence to separate out your signal to combat systematics. So this is ongoing at Berkeley right now. So with that, let me go to the last part of my talk, which is cosmological sensitivity, which is an extremely important part of the story. So here is the fact, right? Let me take my my particular story where I have A mu psi bar gamma mu psi. That is the usual linear quantum mechanics. And now I've added this nonlinear term, which is the expectation value of the A mu operator in the quantum state chi. And let me do something unusual, but not unusual. This is just sort of linear, this is just quantum mechanics. What I'm going to do is I'm going to take the state of the universe to be a superposition of our world U, okay, with some coefficient alpha, and beta times some other quantum state. Okay, I usually call this a multiverse, but I just mean that alpha U is my world, but I'm sitting here at this point in space and giving this talk. M is another world where this could be empty space, right? I'm allowed to think about these kinds of universal superpositions in quantum mechanics. Let me now compute the expectation value chi A mu chi. That is now alpha squared U A mu U plus beta squared M A mu M. U is the world where I'm sitting here doing all these things. M is some other world. I have no control over what it is. Now, here is the extremely important point, right? In linear quantum mechanics, I never care what the value of alpha is ever. right? We never worried about this so far in our lives. So specifically, it could even be that in the quantum mechanical superposition of our world, alpha is 10 to the minus 500, right? We've never worried about it because in linear quantum mechanics, it is a statement that I know that the quantum state U and alpha U evolve the same way, right? That is linearity. So the effects of alpha on linear quantum mechanics are completely irrelevant. It never matters. But in non-linear quantum mechanics is extremely important because if you think about all the laboratory experiments I'm talking about, where I'm sitting here creating a laser, doing all these things, they all, of course, only exist in U. They don't exist in M. M I don't control at all. Now, if it happens to be the case that the Almighty, for whatever bizarre reason, placed me as a tiny part of the superposition, but alpha is extremely small, no matter what I do in the lab, and no matter how large this parameter epsilon is, right, I cannot undo the effect of a small alpha because my physics responds by the expectation value, and that expectation value comes with a small value of alpha square sitting up front. So if alpha is 10 to the minus 500, no matter what the value of epsilon, I will not be able to discover this at all through any of these laboratory experiments. Very different from linear quantum mechanics. Local exploitability of nonlinear quantum mechanics is determined by the initial conditions of the universe. If the Almighty placed me with a small value of alpha, I can never discover this theory. It's a huge difference from linear quantum mechanics. You could ask this game, is it possible somehow for me to boost this effect, right? Can I do something where I condition this operator based upon my presence in this particular universe? So I could take this operator chi mu chi and divide that by U O U, where U is the specific quantum state I'm in, and O is some operator that I can create. But the crucial point is that I can never construct such an operator because the environment I'm talking about is not local, right? The environment is the entire world that I'm entangled with. So I cannot really construct a local projection operator in order to boost these effects, right? So you cannot boost nonlinearity in doing this. But this is, I think, a generic feature of nonlinear quantum mechanics. So quantum mechanics itself could fundamentally be nonlinear in some way. But if we happen to be in a tiny part of the superposition of the universe, we will never find these effects. And in fact, inflation predicts this, right? In inflationary cosmology, right, we actually think there's an enormous number of universes being created by inflation. So inflation could automatically, dynamically place us in a universe where alpha is very, very small. But then one can ask, are there effects that persist even in the limit of extremely small alpha? Okay. What I'm telling you right now is that inflationary cosmology may lead to a situation where all of the laboratory effects of nonlinear quantum mechanics are zero, even though the theory is fundamentally nonlinear. Okay. So in some sense, inflation may have explained why quantum mechanics is observably nonlinear. But we can ask, observably linear. But we can ask, are there things you could still do that will tell us about the fact that quantum mechanics is fundamentally still nonlinear? In other words, are there effects that persist even in inflationary cosmology when alpha is extremely small? So the key point here is that what I need, right? I need some expectation value that is non-zero. In the inflationary cosmology, of course, all these expectation values are supposed to be homogeneous and isotropic. That's what you get from inflation. But obviously in inflationary cosmology, things can still evolve in time, which is why we see that in our world. So what we need is a field that is homogeneous, evolving in time, but still isotropic and has a non-zero web. There is one such web, which is basically the metric. The metric has a non-zero web across the entire superposition. So now if I think about gravity, I now have G mu nu, I put this epsilon times this expectation value, right? This expectation value is now non-zero, even in inflationary cosmology. And that can now do something extremely interesting, which is that, for example, if I take my standard Schwarzschild metric, okay, that I'm used to looking at for an isolated body in the universe, right? I have my standard metric created by my local matter, that is the usual Schwarzschild metric. And now I get this expectation value also, this chi, G mu nu chi. And this guy doesn't, of course, care about my local matter, right? This is just the average metric of the universe. And there is just this negative dt squared, dr squared, whatever. Local matter will now respond not just to G mu nu, it will respond to G mu nu plus epsilon times this thing, which now means the metric that local matter sees gets modified ever so slightly. if you do all the renormalization correctly, what you now see is that at order RS over R squared, this epsilon term appears. Okay. So funnily enough, this now shows up as a second order GR correction. Okay. RS over R is the first order GR correction that sits in front of the dr squared term. This now becomes a second order correction to general relativity. So funnily enough, right, even though we have probed GR locally on the Earth, those are all like, pretty small because we have only probed GR, the weak field, through terrestrial solar system experiments. This is only now in humanity, we're actually probing strong field GR with things like LIGO, right? So we're actually now thinking about how maybe at LIGO, things of this sign, you can now start beginning to probe order epsilon RS over R squared terms that are showing up essentially because of this other metric interfering with you. Very importantly, this thing also has extremely interesting implications for the black hole information problem, because now if I have this kind of metric pollution, what will actually happen is that the horizon of the black hole now becomes a special point. So in the normal Schwarzschild geometry, the horizon is not a special point because the place where GTT goes to zero, naively you think that's a singularity, but the place where GTT goes to zero is exactly the same place where GRR diverges. So if you compute the determinant of the metric, for example, that is now some non-zero number, that's some finite number, and therefore you realize it's a coordinate singularity. But now when you actually have this kind of superposition happening, the effective metric is this particular sum, what you notice is that the place where GTT goes to zero is no longer the place where GRR diverges, which basically means the horizon has now become a special point. So effectively what you end up creating is a singularity, if you will, at the scale of the horizon, which basically creates something like a firewall, an actual physical firewall. This is not the kind of firewall that people mumble about. This is something that I call it. It's an actual singularity that you end up getting at the scale of the horizon. Again, we are now at the first time in humanity being able to actually probe this kind of physics with experiments like LIGO. So with that, let me conclude. I don't think I've gone too much over time. In fact, I'm finishing exactly on time, which is a surprise for the stock. What I have hopefully convinced you is that it is in fact the case that quantum field theory can be generalized to include nonlinear state-dependent evolution. It seems like the structure of the theory allows you to do this. Very, very interestingly, conventional tests of quantum mechanics in atomic and nuclear systems, where we don't care, where we have so far not spent time localizing the wave function of the system, those tests are not constraining nonlinear quantum mechanics. However, there are in fact straightforward set of experimental tests possible, and some of them are even being done right now to probe nonlinear quantum mechanics. But very, very importantly, cosmological sensitivity means that there are a variety of new probes one actually requires to think through this full story here. And with that, let me stop. Thank you.